We are on to solid state chemistry. So we've spent some time talking about gases and how molecules behave in the gas phase. We've spent some time talking about liquids and solids, intermolecular forces, and how these things will behave in these senses. But we want to kind of expand on solids themselves and kind of delve into the solid structures. We understand they're being held together by different types of intermolecular forces, but what's really going on, what structures exist, and what can we delve from this information? So first, just as an overall chapter focus for here, we're looking at molecular and crystalline solids, melting and boiling point properties and trends. So some of this will be review. We've seen, these trends between melting and boiling point already. We're going to kind of expand upon that. Crystal lattice. We've dealt with crystal lattices. We've seen this in previous chapters. We're going to kind of expand on that again. The unit cell. Born-Haber cycle. This is actually from Module 10. But we didn't cover it there. We're covering it here instead. But if you're looking for the chapter, it's covered under Module 10 chapter material. And it's connected to our crystal lattice, which is also, we're also exposed to crystal lattice in Chapter 10 or Module 10. You've got crystal systems. There's different types of crystal systems. We are going to focus on simple cubic, body-centered cubic, and face-centered cubic structures in this unit. But I need you to recognize there are other types of crystal systems, even though you will not be doing calculations for those systems. You need to be able to recognize them, but you're going to be doing calculations for simple cubic, body-centered cubic, and face-centered cubic. We have network solids and covalent solids, and we're going to discuss band theory. So for Module 13A, we're really going to kind of start going in and talking about these different types of bonding. So you need to be able to compare and contrast bonding types and physical properties of ionic solids, covalent solids, atomic solids, network solids, and metallic solids. So we've got different types of solids going on here, and I need you to be able to recognize what they're doing, why they exist, how they're going to form, and be able to start predicting when you're going to find these types of solids. I really like this chart from your book. It breaks it down very nicely. So first, crystalline solid. We don't really think about it, but these compounds are forming crystals. If we can get down to a small enough level, we can actually see these crystals. We have to use special instrumentation for this. Most often we'll use something called an X-ray diffractometer, and it actually uses X-rays to penetrate the crystal structure so that we can actually see the overall structure of the molecule, the structure of the compound. It's really kind of cool. It's a really neat technique to be able to do, and you can do it for crystalline or you can do it for powder. So how we actually figure out these things, we use high-powered instruments. Within crystalline solids, we've got molecular solids, ionic solids, and atomic solids, and then they can be broken down further as well. Molecular solids are molecules, your composite unit, meaning what makes up that solid is a molecule, such as water. It's a water molecule. These have low melting points. They can be held together by IMFs. They can, IMFs, specifically LDFs, dipole-dipole, hydrogen bonding can happen, but they tend to be weaker overall forces. They have lower melting points and also lower boiling points because they have the weaker IMFs. We also have ionic solids, which is a formula unit, is your composite unit. So your cations, your anions. If you have an ionic compound, you've got cations and anions. So here we see table salt, so like sodium chloride, Na+, Cl-. We talked about lattice energy in Module 10. We know that the smaller it is, the higher the lattice energy. We know that the charge also increases, higher the charge increases our lattice energy. So if we had, like, say, magnesium oxide, MgO, magnesium is +2, oxide is -2, that's going to have a higher lattice energy because it has a higher charge to it. We also know that charge trumps size. Charge matters over size, meaning that it will lead to a higher melting point, higher eventual boiling point of these molecules. But ionic solids are just that. They're solids that are made up of formula units of ionic compounds. That opposite charge attraction, that positive cation, that negative anion. We can also have atomic solids, where the composite unit here are just atoms. So we can have non-bonding, metallic, or network covalent atomic solids. Non-bonding would be things such as your noble gases. They are held together by LDFs only. so your dispersion forces only. And they have low melting points, so such as solid xenon. We do see these start to form solids if we get low enough in temperature. Again, the larger that molecule is, the more likely you'll find it in a solid phase at a higher temperature because you've got your polarizability going on. So all these concepts that we've talked about, all this terminology we've talked about is all coming back into play. You've got metallic solids. These are your metals. They're held together by metallic bonds, and they have varying melting points. It depends on the compound itself what its melting point will be. We've talked about metallic bonding some with the sea of electrons, the cations floating around with the electrons just kind of interdispersed around it. And then we can also have network covalent. These are held together by covalent bonds. And these have high melting points. So this is what we see for like quartz, which is silicon dioxide. So network covalent will actually form covalent bonds, and it takes more energy to break up these covalent bonds. They're not just intermolecular forces holding them together, they're actual bonds holding them together, and they form large structures. So again, silicon dioxide or quartz does this, graphite does this. We'll see some other examples as well. If you hear me talk about the word amorphous itself is just a way to describe something that does not have a specific shape. So molecular solids. Why do molecular compounds have lower melting and boiling points? Well, your melting and boiling point, a melting point or a boiling point involves breaking the attractions, specifically the intermolecular forces between the molecules, but not the bonds of the atoms. So again, melting and boiling, breaking your attractions, which is your IMFs, between molecules, but you're not breaking bonds. Covalent bonds are strong. Attractions between the molecules are generally weak. Now, it's all a relative game there. Covalent bonds are stronger than intermolecular forces. But it comes down to things like polarizability, polarity, that can overcome and become strong enough. That's why things like I2 are solid at a room temperature, because it's so polarizable that even though it's only got LDFs as its force holding it together, it's strong. It's holding many of those together. So covalent bonds are strong. The attractions between the molecules are generally speaking weak. The polarity of the covalent bonds influences the strength of the intermolecular forces. So I need you to think about, it's this balancing game between how polarizable is it? What is the polarity of that bond? Is there polarity? Is there not polarity? What are the bonds it has versus what intermolecular forces it has? And that's going to help you determine what's going to boil faster or what's going to boil at a lower temperature or a higher temperature, what's going to melt at a lower temperature or higher temperature, etc. So for example, pentane, C5H12. If you draw out pentane, you've got 5 carbons in a chain, and each carbon has 4 bonds. So it's bonded to other carbons, and then it has enough hydrogens to give itself, every carbon, 4 bonds, which ends up being 12 hydrogens. The molecules here, this itself, this is covalently bonded. But this is attracted to a second molecule through attractive forces, specifically London dispersion forces. This is nonpolar. Carbon-hydrogen is considered a nonpolar compound. Its polarity difference is 0.4, which is just on the cusp of nonpolar. So this is held together by LDFs only. They are a weaker force. They have strong covalent bonds within the molecule. These are your covalent bonds. These are strong. But attached to or attracted to another molecule, the attractive force here is weak because this is your LDF. Weaker intermolecular forces between your molecules, strong covalent bonds within your molecule. So I need you guys to keep track of what's happening between separate molecules versus what's happening within a molecule. and crystalline solids. A crystalline solid has a crystal lattice with a regular repeating 3D pattern of particles. The unit cell is the smallest unit showing this pattern. The unit cell repeats over and over to give the macroscopic crystal structure of the solid. The unit cell can start anywhere within the crystal and result within the same unit cell. When allowed to cool slowly, the particles in a liquid will arrange themselves to give maximum attractive forces to be able to minimize their energy and form their crystal. This is looking at your lattice energy. So if we look at the chart down here, we see each particle in the unit cell is called a lattice point, and lattice planes are the planes connecting equivalent points in unit cells throughout the lattice. Each one of these, make this so you can actually see it a little bit better. Here is a unit cell. Here is a unit cell. Here is a unit cell. You can do this over and over again. There's the unit cells throughout this whole thing. You can start at any point and you can draw the unit cells. So each particle, each point in the unit cell is called the lattice point, and the lattice planes, each side, are the planes connecting equivalent points in unit cells throughout the lattice. So lattice point, lattice plane. And you can have those unit cells. These unit cells are the smallest repeating unit throughout your crystal structure, and they will keep repeating.